Okay, so today's video is on salts and more specifically how to make a pure dry salt. But before we start, let's do a quick quiz. So what I'd like to do is pause the video now and have a go at these 5 questions. So I'm going to restart and go through the answers in 5, 3, 2, 1. Okay, so actually pause the video and do these questions, right? I know that you didn't bother pausing it. So pause it, do the questions. I'll go through the answers now. So what's the pH of an acid? Less than 7. So 7 is neutral, anything less than 7 is acidic. What ions are found in an acidic solution? Hydrogen ions, H+. Acid plus base makes salt and water. What does soluble mean? Something that's soluble means it dissolves. So insoluble means it doesn't dissolve. And what type of reaction is question 3? So that is a neutralization reaction. Neutralization reaction. So going back to title for today's lesson, how to make a pure dry salt. So there's a couple of methods. Firstly, let's just talk about what this means. So pure means it only contains one type of substance. So the only substance we'll have is whichever salt we're interested in. Dry, so there's no solvent left, there's no water left in it. So pure dry salt. And going back to quick quiz, how do we make a salt? Well, we react an acid with a base. So what we're gonna hopefully have. So we've done our experiment and we are going to have, that's a beaker by the way, so we're going to have a beaker and that beaker is going to have some water in it, H2O, and it's going to have some salt in it. So lots and lots of water molecules, and dissolved in it would be the salt. So not quite pure and not quite dry yet. So then what we'll have to do is slowly evaporate all the water, and then if we evaporate all the water away, the salt won't evaporate, and then at the end you'll get left with the salt, which is great. But for that to happen, there needs to only be water and salt left. And that's a little bit of a problem when we look at what we actually need to do this reaction. So we just said we needed an acid and we needed a base to make salt and water. So what that would mean is if we didn't do this reaction perfectly, we might end up with a situation where we've got our beaker, we've definitely got some water in there, we've definitely got some salt in there, but if we added too much acid, we'd have some acid left in there as well. Or if we didn't add enough acid, so we didn't have quite enough acid, that means we would end up with some base left. And if we've got either any acid or base left, when we evaporate all the water away, what we end up with is, yes, we end up with our salt, which is what we want, but we will end up with either some base mixed in there or some acid mixed in there, which means it's not pure. And there's 2 categories of doing this. So the first one we're going to look at, which is the simplest, is if we are using an insoluble base. So this is the simplest one. So if we're using an insoluble base, so we have our acid, we had our base, and then, sorry if you can hear any background noise, I've got some construction work happening about 4 feet away from where I'm recording this. So we've got our acid, we've got our base, that's going to make salt and water. But the beauty of this is that the base is insoluble. So all you do is you add, it's called excess. Basically, when you add excess, it means you're adding far too much. So you're adding excess base. So we've got our acid, got our acid in our beaker, and then we add in loads of base, absolutely loads, far more than you would ever need. So it's definitely in excess. But the perfect thing is, because it is insoluble, it keeps reacting with the acid until there's no acid left. And then as soon as there's no acid left, well, we keep adding that base, keep adding it. There's no acid left for it to react with, and so that base is insoluble, so it just sinks to the bottom. And then if you remember from the unit on separating techniques, how can you separate out something that's insoluble? You filter it. So you get your filter funnel with your filter paper, pour all that in there, and then so the base, the excess base, is kept as a solid caught by the filter paper, and then what drips down into the bottom here is just salt, which is dissolved, and water. So how do we turn that salt and water into our pure dry salt? Well, we crystallize it. We let the water evaporate and it leaves the salt behind. Perfect. So it's as straightforward as that. If the base is insoluble, you just add excess base, because that definitely means all the acid is definitely gone because you've added loads of the base. How do you get rid of the excess base? You filter it. So then we've definitely got rid of all the base, and all that is left is salt and water. Brilliant. Perfect. Evaporate the water, crystallize the salt, pure dry salt. Done. However, if the base is soluble, this is where it gets a little bit more tricky. So if the base is soluble, so soluble base, that does have another name. You can also call that, I can't spell it though, a base that is soluble, it's called an alkali. It's slightly more trickier. And what you need to do now is, we're still going to have acid plus base. Remember, this base happens to be soluble. It's going to make us salt and water. But we need to absolutely be sure, the only way of doing this, we can't filter out the base anymore because it's soluble. So if we add too much base, yes, we'll have used all the acid, but there'll be base left at the end. If we add not enough base, there won't be any base left at the end, but there'll be some acid left, which is a problem. So we need to make sure these are mixed in the perfect volumes. And we do that by doing an experiment called a titration. And how titrations work, and you measure them incredibly accurately. You have a piece of equipment, and I'll make sure that on the assignment I include some photos of this, or you can just go and Google it. There's a bit of equipment called a Buret. So here's a picture of an actual Buret I found online. You can see the zoomed in portion of the tap where you can twist that handle to open it and let liquid out, or to close it and stop it, and you can see the markings up the side. It can be used to measure any volume incredibly accurately. It's a long, thin cylinder, and at the bottom it's got a tap. And it's got markings all up the side. And it lets you measure the volume of something incredibly accurately. So we've got our Buret, we have a little flask, little conical flask at the bottom, and then we get something else called a pipette, which also lets us measure the volume of something incredibly accurately, and then you connect that to like a pipette filler, like a bit of a syringe sort of thing really. And so the idea is, and it doesn't matter which way around you do this, the idea is you use, so that is the Buret. So here's a picture of a pipette I found online. It doesn't have the syringe sort of plastic pipette filler attached to it. But whereas the Buret measures any volume very accurately, the pipette measures one specific volume. So in this example, it's a 25 centimeter cubed pipette, and so you use it to measure 25 centimeters cubed exactly each time. And that is the pipette. And so you take the pipette. I'm gonna, even though these, in reality, these are all totally colourless, but I'm gonna I'm going to draw them as coloured so you can kind of get an idea of what's going on. So you take the pipette and you fill it up with, let's say we fill that up with our base. And we use the pipette to measure something incredibly accurately. So let's just say, for argument's sake, we put exactly 25 centimetres cubed of base in our pipette, and then we drop that down into our conical flask down here. Okay, so the pipette, now empty. Right, then inside the Buret, we put our acid. Okay, so we've put our acid in there. Right, so we've got acid in there, and then this tap, you can open this tap really slowly, and so one drop at a time, the acid drips through. Okay, I'm going to rub this out and just draw it out again quickly because I don't want the colours there anymore. So we've got, remember, our Buret, long, thin cylinder with all these measurements on, so it's possible to be very accurate. And then it's got a little tap at the bottom where you can control how much it's getting released. Right, so down here we've got our base, in here we've got our acid, and we're going to add this a drop at a time until they've perfectly reacted. And then so when they've perfectly reacted, we stop the tap. We can look at, you know, so we know exactly we've got 25 centimetre cubed of base in there perfectly. We can look at this. Let's say this reading says 15 centimetres cubed. And then we do our experiment and it goes down to here. And we look there and that one says, I don't know, 55 centimetres cubed. And we go, oh, how much acid did we add? So we do 55, take away 15, and we can say that we've added exactly 40 centimetres cubed of acid for this to react. Now I've left out a crucial step, which I will go through in a second, but what this would mean is we know we need to add exactly 40 centimetres cubed of acid to 25 centimetres cubed of base. But how do we know that? We add something called an indicator, because the base will have a pH of bigger than 7, the acid will have a pH of lower than 7, and when they react perfectly in exactly the right amounts that we need, they will have a pH of 7. So we use an indicator to show us that. Now we don't use universal indicator, which is something you've probably heard of a lot of time, and you know, it goes red in a really strong acid, then yellow, and then green when it's neutral, and then sort of bluey purple when it's in alkali. The reason we can't use universal indicator, if we put it in here, yes, it would be blue. And then as we drop in, it would go from blue, and it would look a little bit greeny. And then if we kept adding loads and loads of acid, it would go yellowy, and then it would go red. But it doesn't have like a definite endpoint. It doesn't have a perfect endpoint. It's very difficult to tell when it is exactly green. You'd be looking at it saying, is that a bluey green or a green? Or is it, have we gone too far? Is it a yellowy green? You need an indicator that's got a definite endpoint. And there are a couple of those you need to know about for GCSE chemistry. So one is called methyl, I'll write that with neater writing so you can actually read it. Methyl orange, acidic, alkaline. So methyl orange, if you add methyl orange to an acidic solution, these give you a definite colour change. So methyl orange is red in an acidic solution, and it is yellow in an alkaline solution. And so the only two colour changes that happen, and it happens with one drop, happens instantly. Or the other indicator, which is easier to say than it is to spell, is phenolphthalein. Phenolphthalein. And phenolphthalein is colourless. Totally colourless in an acid, and it's bright pink in alkaline. So let's say, for argument's sake, in our example, I'm going to use phenolphthalein. So I've got this all set up. Let's say, let's rub these out. Rub that out there. So this is my Buret. I can see that at the moment the acid is at the level that says 15 centimeters cubed. In here I used a pipette to measure this in. There's exactly 25 centimeters cubed of base. And then I'm going to put some phenolphthalein indicator in there. And because it's a base, if you remember back here, so base is alkaline condition, so phenolphthalein, it'll be pink. So this will look bright pink. And then I open the tap and I add my base in. Sorry, I add my acid in, 1 drip at a time. And eventually, when there's the perfect amount of acid and base and they've reacted perfectly, this will be at pH 7. And the phenolphthalein will go in the space of 1 drop. It will turn from pink to colourless. And then I quickly stop the tap. So let's say that the acid's got down to here. And now it's at 55 centimeters cubed. And this has gone colourless, right? So now I know, right, for 25 centimeter cubed of base, I need that minus that. I need to add 40 centimeters cubed of acid. So now I can make my pure dry salt. Except it's not pure because there's an indicator in it. It's still got phenolphthalein in it. So I do this experiment again, but I do not add an indicator this time. I've just got to trust my judgment from my previous thing. So I throw all this away, put fresh acid in here. I've got my base in here. I use the pipette to add exactly 25 centimeter cubed of base, and then use the Buret to add exactly 40 centimeter cubed of acid. And then I will know that I have reacted perfectly in the perfect proportions. I've added acid and base, and I've made salt and water. So there won't be any acid or any base left because my titration reacted them together perfectly. So all I'm left with is salt and water, and then I can evaporate the water away to crystallize the salt. So how to make a pure dry salt? Well, it all depends on what you're reacting. If the base is insoluble, lovely, nice and easy. You just add excess of it and then filter it away. Then you've got rid of your base and you've reacted all your acid. If the base is soluble, that is when you have to do a titration. I'll do 2 very quick examples of these and we'll do a quick recap on state symbols. So I'm going to react copper oxide with sulfuric acid. And copper oxide and sulfuric acid is going to give me as my salt copper sulfate. So copper sulfate and water. Now copper oxide is insoluble, so I add excess copper sulfate. So when I've added excess copper sulfate, sorry, I'll start again. I've said copper sulfate a lot. Copper oxide is what I meant. Copper oxide is insoluble. So I can take my sulfuric acid and add absolutely boatloads of copper oxide. Loads and loads and loads of it. Excess of it. So much copper oxide that it's reacted with all of the sulfuric acid. And then what I'll be left with in my beaker is just water. I'll be left with my salt, which is copper sulfate. And I'll be left with a huge pile at the bottom of copper oxide. So then I can stick it through a filter paper. That's my not so good funnel with my filter paper. So I pour all that in there. And all of the excess copper oxide, because it's insoluble, gets caught in the filter paper. There, and I can just bin it. And then here, I just end up with the water and the salt. And then I can evaporate the water, crystallize the salt. Brilliant. And this is all because the copper oxide is insoluble. For the other one, so let's say I'm going to make sodium hydroxide. Do you know what? I'll do this one as symbols. Sodium hydroxide, NaOH. That is 8Q, aqueous. That means it's dissolved in water. I'm going to react it with hydrochloric acid, which is aqueous because it's dissolved in water. And that is going to give me sodium chloride, which is aqueous, dissolved in water. And it gives me water, which is a liquid. Okay. This time my base is soluble, so I can't add excess. I need to make sure these are perfect. So I do a titration, which is where I have my Buret with a tap on the bottom. Remember that's spelled as a Buret. I have my conical flask. I put my indicator in there. And then I have my pipette, which is like the little fancy syringe on the end. Right, so in this example, I'm going to put my hydrochloric acid in the pipette, and I'm going to put that in there. So I'm going to measure out exactly 30 centimeters cubed with the pipette. Then in the Buret, I'm going to put my NaOH. I need an indicator. So this example, I will use methyl orange. So I put my methyl orange in there, and I put my acid in. So the eagle-eyed viewers will have noticed almost seamless jump cut there, because I didn't realise that my phone had stopped recording. So I'm going to try and pick up where I left off. So we've got acid in here, which has been measured out from the pipette. We added methyl orange as the indicator. So methyl orange, when it's in acidic conditions, is red. We've got sodium hydroxide, NaOH, in here. This is our soluble base. And so we look at the measurement of how much NaOH we've got. Let's say it's on 80 centimeters cubed. Then we start adding it a drop at a time, and we're watching this methyl orange, and as soon as it changes colour, we know that it has been neutralised to yellow, so we quickly stop the tap. If we leave it running too long, we'll have added too much of this, so we need to stop it instantly as soon as it changes colour. Let's say it's dropped down to here, and we go, oh look, this is now on 90 centimetres cubed. We can work out we've added exactly 10 centimetres of NaOH. So then we pour this away, we start again. This time without the indicator, and we know we add exactly 30 centimetres cubed of our acid. We add 10 centimetres cubed of NaOH. So then the acid and the alkali have reacted perfectly together, leaving us with just salt and water, and we can crystallise the salt. So how do you make a pure dry salt? It all depends. Your acid will always be soluble. It all depends if the base you're using is soluble or insoluble.